Alright, I'm popping videos like I'm popping pills now. I don't pop pills, but you get the idea. So, I'd like to jump straight to circuits, but first I need you to realize that before I knew how to design things, I needed to understand them. And as a side note, academic stuff like textbooks is really bad if you want to build practical things, because academics aren't really interested in building practical things. They're more interested in the system theories side of things. So I'm sorry, but I'll have to go through some theory, let's say. Let's just look at something. For example, if I want to if I want to show other people how circuits work, or even to remind myself in a good way, in a way easy to read way, I'll use the schematics. And Falstad's circuit sim is nice to do schematics. You can do away with all the coloring and make it black on white. Oops, not this, I mean this. And that's actually good enough for whatever practical process we might want them. Let's just give it color so that I can show some other stuff now. So in schematics, we use symbols to show where to put things in relation to others and what things connect to what. Components like this resistor can be in pretty much any geometry, but we have to find here a system which, when you draw on paper or on computer screen, we can tell quickly what the system is doing. And also we want to be able to draw it quickly if we are drawing on paper. So there are these symbols which they are just there to as representations to remind us what that thing is supposed to be. For example, this is the symbol for a voltage source, a simple voltage source, battery, more specifically. This is a resistor, as I told before. There are 3 resistors there. This one is 20 kilo ohms. We don't need to put the ohm there, because if the symbol is a resistor, we already know. We only care about the ohm value of it. This is 10k. This is 1 for 1 ginormous, actually giga ohm, but whatever. This is pretty much like what we would call an insulator for this kind of voltage. Can double click it, I think. Come on. Okay, and there's the voltage it is outputting, or you can read it here. As you can see, if you go to the resistor, the big one, you can see how many amperes or intensity it's going through it, and this is really low. 1 nanoampere might very well be lower than the noise picked up by the circuit from radio frequencies and static electricity. So for any practical purposes like turning on a lamp or sensing a signal in electronics, that the signal or such, this is useless. This amount of current doesn't give us enough power to tell the difference between some action the circuit is doing and noise, from random noise all circuits have. Yeah, this one, it's actually 20 and 10 kilo ohms is kind of high for a 5 volt, but it pretty much works. When we design a circuit, we want to consume the least power possible. That means the smaller current, and smaller currents come from higher resistances. So the bigger the resistance we use for our circuits, the better. It means more energy efficiency. But there's this catch, which I've already mentioned, which is all real-world circuits will have noise, will pick up electric fields from the environment, the air. The nature produces a lot of electric fields, so does other circuits of other machinery. For example, doing circuits near a computer, we might expect our circuit to pick up signals from the computer. So we can't use too high of resistors, or the power going through them is so low that we can't distinguish from the noise we are picking up. And what power is that noise? Well, it's hard to tell, depends on whatever whatever environment you are in. For example, if you are near a computer or a microwave machine, your circuit will pick up more noise, but so you would need smaller resistors to make the circuit work as you expect it. And that's another point. Circuits will always work however you connect them. They might not. The issue is that they might not work as you expect them. And when that happens, what you call that a malfunction, I guess, but maybe you can think about it as a misconception. Maybe your understanding towards the circuits has some underlying fallacy, and it's important to figure out what that is. So when I'm troubleshooting a machine, either electronic or not, I have in the back of my mind, I've always all the thought that maybe I'm understanding it wrong. Maybe what I thought would happen, or how I think the mechanism works, isn't how it really is working. So yeah, these are most of my notes about circuit design in general, or even other kinds of non-electronic devices. Here's an interesting thing. We don't usually draw circuits with these symbols. Wow, what a shocker. I'm just using this battery symbol because it looks like it's more reminiscent of how you'd build it in real life, where the battery has the wires, the terminals. But this kind of way of drawing things will get really cumbersome when you have a lot of components. So a way to simplify it is, first, we don't need a battery symbol. We already know that if our circuit works, it's most likely connected to some power supply. We imply that. We just use just put a label to say what I expect, to say that we expect a constant voltage at that point. And likewise, we don't use this wire, or you don't even need this wire. All circuits will have a point to which everything connects, and that isn't at 5 volts, because lots of circuits have various voltage levels. The only thing in common between all systems in a circuit is the zero, what we call zero, the reference zero. And we call that ground, or, as we may guess, the common connection, because these two are supposed to be common to each other, or have the same, or in other words, be connected to each other. So this is the ground symbol, or common symbol. It's like you can think about it like a portal, a teleportation portal. A wire going this way will also come out this way, as well as it will come out of the other terminal of the battery. Ta-da! This thing is pretty much like the same, just that you have to note that you have to realize that if we have several voltages, for example, we can have a bigger battery or two batteries which add up the voltage, you have to consider that these two wires are together, even though this one will now be 10 volts. Oh, yeah, 10 volts, right. this is 5, come on, this is 5, this is 5, and this is, therefore this is 10 relative to this common point, which we called 0. If you connect this thing here, of course it will be 0 volts. As well, it will be 0 volts. This is my multimeter probe. Now, I'm misleading here a bit, because if you check out on multimeters, on real world multimeters or voltmeters, they have 2 wires, not just one. So where is the other one? This one we used to check the voltage at whatever position, so it will measure. Let's clear out the simulator wasn't designed to work in this way, but so now we clear that up. So we stick it here, we measure 5, we stick it here, we measure something else, we stick it here, 5 again, but here it's 10. You can guess it. So where's the other terminal of the multimeter or voltmeter? It's, well, ground, of course. You can consider this the other point of the multimeter. So wherever we have this common, wherever we have this portal, will lead to a multimeter too. And so here's an interesting part. What if ground is actually here? Like if we put the second terminal of the multimeter in this point, it won't like it. I actually not sure why. Let's clear one of these up. Maybe that's why. Okay, now it works. So now this is 0 volts. It isn't 1.27 or whatever. Yeah, with voltages, one thing you have to realize is that voltages are relative. You always need 2 terminals to make a voltage sensible. And the place where everything is connected in common, because it's what we are considering 0 volts, will be where we use this symbol. If you want, you might consider this. You might want to consider this point of the battery the 0 volts. But in that case, see the color change. We now have here -5 volts. It's below what we call 0. Whatever we call 0, it's below that. That's a powerful thing to understand when you check later with more complex circuits. So let's use a proper way of, a more practical way of drawing, a way that spends less ink and paper. Oops. It's this way. Now, you notice that giga resistor. It's just another way to tell you that it's too high of a resistance to care about, so we don't draw it at all. The output of a circuit can't be just one wire like this seems to show, because there won't be a voltage difference. There's whatever the voltage is, but relative to what? We need the ground of this, whatever this thing is leading to. In this case, this thing is leading to this oscilloscope. And as you can see, it's measuring 1.67 volts. Remember, the other probe of the oscilloscope is also here, connected here, but we don't draw it because it's implied. Yeah. It's common to everything. So, another very powerful theoretical understanding is the concept of a voltage divider. One of the everything in an electronic circuit is all electronic. Let's put it another way. What are we trying to do when designing an electronic circuit? Most, if not all, electronic circuits are devices which change their resistance depending on whatever action you are doing on them, whatever you want out of them. So as you can see, we are having here 1.67 volts at this point because the values of these resistors make it so. If this resistor is higher, like 20, the voltage will change, and so this is higher, so the output seems closer to the 5 volts, therefore a higher voltage. If this resistance is higher, like 50, then the output seems closer to the ground, so you have a lower voltage. And so what else could I tell you about that? So yeah, well, one thing that might mislead a beginner is that resistors don't actually change a voltage. You see, 5 volts when it's just a resistor. What actually changes a resistor is a kind of network or arrangement we call a voltage divider. As you may understand why we call it that. It's dividing the voltage into 2 chunks, and this chunk here between this point and this point is 1.43 volts. The voltage between this point and this point is nothing really, just picking up the 5 volts because it's just one resistor. So one way to change the resistance of or to control the resistance of circuits is using a voltage divider. Of course, just using the plain simple resistors makes for a boring divider. We need a device which changes its resistance, as I told you before, to make it act according to some environmental thing. One of the simplest ways of changing a resistance is with a capacitor. So a capacitor is a device which changes its resistance depending on time. Let's reset the circuit so the capacitor is current flow, so it's at a zero. How do I explain this? Well, you'll understand soon enough. As you can see, the voltage will rise slowly as the capacitor will seem like never increasing resistance. The inductor is the same thing, also a time-sensitive resistor, but it works in reverse. It will look like a really low resistance, and its resistance will it will look like a really high resistance, but its resistance will climb as the voltage drops, as time passes. And this is really powerful. Most of our circuits, most of the complex circuits, most of the circuits which do smart things will need some sort of time sensing. Inductors and capacitors are the ways to sense the passage of time. We don't usually use inductors for that because, as you can see here, the value is quite large, and here the value is quite small. It's much cheaper to make capacitors than inductors. When you need to do something that looks like an inductor, you can trade these two. Whoa. And as you can see, it will, let me put this into frame. Alright, it will reverse the behavior. Cool, huh? And likewise, the inductor can be reversed to do a capacitor looking thing. So capacitors and inductors are really the same thing, just working in reverse. In mathematical speaking, capacitors work like are integrating machines, and inductors are derivating machines, or differentiating, if you want. I'm not sure about the terminology there. I think it's confusing. How they do what they do, it's a matter for another talk, but when you are designing a circuit, this is the most important thing to realize. Every circuit is a voltage divider of some sort, and a way to change the voltage through time is by, or rather, the way to change a voltage through some action is by changing one of the resistors by something else that reacts to something in the environment. In case of inductors and capacitors, that is time. Capacitors and inductors are, in other words, time-dependent sensors. And so, other kinds of sensors exist. For example, let's see, a touch sensor, as it's it's what we call a switch, a mechanical switch, for example. So when we press the switch, the circuit knows we are pressing it, so that's a form of sensor. Or as you can see, the voltage varies a lot. We can do a square waveform like that if you want to. Let me just make it simple for me. It's now a momentary switch. Ta-da! Look at the duty cycle. It's like PWM or something. So, what other sensors exist? For example, there are temperature sensing sensors. Those don't really have an interesting name, but they are, sometimes we call them thermistors, but you can also use the temperature dependent resistor if you want. What else? There is a potentiometer, which is just like a plain resistor, but we can change it with your hands. And as you will see, it will act very much like the capacitor with varying degrees of resistance. Let's see if we can get it to work. Well, it's a really high voltage. Let's fix that. Really low current, I mean. Let's put this higher current than that thing there. Higher resistance, I mean. So we are closer to the 5 volts. There you go. So as you can see, oh, it looks like what inductor is doing, kinda. Well, in a weird way. So a capacitor will start like a real large resistor, like now, and its resistance will rise. And as it rises, it will get slower. Of course, when you control it manually, you don't need to do these arches, don't need to do these curves. You can go really fast or really small, can go linear if your hand is that good, kind of. Guess what? You can have things that are like potentiometers, but which aren't controlled by your hands, are controlled by other signal from somewhere else. Like that would be a transistor. Well, I don't have a separate voltage signal here now to show that, but you can trust me on that. Transistors are resistors which change value depending on some other voltage. There are all kinds of sensors, but they all work this way. They are some sort of resistor which changes its value depending on something in the environment. Can be light, can be temperature, can be time, can be other voltage, whatever. That's it for today. I guess it's enough.